Okay, good morning. Right, so first we will do the data management. So today we move on to our third topic, that is database indexes and tuning. Okay, so this topic I have uploaded 2 notes. That is your UCSC note and also our own note. But I will be mostly using the UCSC note. Use our note as a supplement. So your main note is UCSC note. Okay. Right. So let's move on. Right. So database indexing and tuning. Right. So remember, when it comes to database management systems, we can look at it as using 3-tier architecture. That is the physical layer, logical or conceptual layer, external or user layer. This is physical or internal layer. This is logical or conceptual layer. So here we have the screens, reports, views. That is what the end users are interested. Here we have the relations and relationships when it comes to relational databases. For tables and relationships, it's a logical thing. And this is where the real data is stored. That is where you have the data files and index files. Right? Data files and index files. So today what we discuss is this aspect of database, the physical layer or the file layer. Okay. So why are we interested about the physical layer? One reason is we want to understand how the database work internally, just like we understand how the computer work internally in computer system subject. The second thing is we can use certain aspects when you understand this, how the data is stored in files and so on. We also have a little bit of, not little bit of, we have a flexibility to use those features for our advantage, especially for performance. So when you know how the data is stored here and different mechanisms, and some of those are exposed to us as database designers and developers, we can select the best combination. So we can influence the database management system to use certain approach, or we can say use this approach, not the other approach. Because for us, maybe the approach A is better performance than approach B, and so on. Okay. So therefore, this is advanced topic because we are looking at the internally how the data is saved in files and so on. So therefore, you don't have to memorize a lot of things, right? You have to remember only few things, but you have to understand at a high level, right? Higher seriousness level. Otherwise, after some time, you will completely lost. You are completely lost. Okay. So therefore, pay attention. And if you have any questions, you can ask. Nothing much to remember, but a lot of things for you to understand. And you have to keep connecting those concepts together, right? And stay with the big picture. Okay. And earlier, I told you this subject was in final year, but you know that when we advance, right? So what we call advanced subject come to the intermediary because we have some other subject in the advanced level. So that is how it goes. Okay. For example, about 10 years ago, computer system subject also was in final year. Now computer system subject is in the first semester one. Okay. So likewise. Right. So we'll look at what are the different file structures, what are the different index structures, and so on in this particular topic. So this lesson on database indexing and tuning. Tuning means increase the performance. Okay. Discusses the gradual development of computer memory hierarchy and hence the evolution of the indexing methods. Here we look into the type of computer memory and types of indexers in details. So at the end of the lesson, you will be able to describe how different computer memories evolve, identify different types of computer memory and the storage organizations of database, recognize the importance of implementing indexes in database, explain the key concepts of different types of database indexes. So these are our topic. First, we have the disk storage and basic file structures. Then we move on to the indexes, like type of indexes, right? Indexes for multiple keys, single keys, other special type of indexes, and of course, how to create indexes using SQL, and also the physical database design in relational database. Okay. So that is the use of the above knowledge. Right. So this part is the easier topic. I will go through this the first part fast because this is something you have learned in your computer system. Right. So you know that we have a hierarchy of memory. Right. Hierarchy of memory. Hierarchy of memory, or we can say hierarchy of storage. Okay. So you have the registries in the processor itself, then the RAM, then your secondary storage, that is your SSD or the hard disk, and then the backup storage or the tertiary storage, right? Maybe CD, right? External hard disk, and so on, magnetic tape, and so on. That is tertiary storage. Sometimes RAM is called the primary storage, then primary storage, secondary storage, tertiary storage. And you know that this is volatile, this is non-volatile. I haven't taken the ROM because ROM is a special case for supporting your system functions. Okay. So that is how you understand storage hierarchy. Sometimes we call it memory hierarchy, but the better word is storage hierarchy. Okay. So why do we need a hierarchy? Because here we have more storage, but it's slower. But when you go up, the access speed is getting higher. One reason is it is getting closer to the memory. The second reason is obviously the technology is superior. Right. So for example, registries, we have only few bytes, few kilobytes, RAM gigabyte level, secondary storage terabytes level, and so on. Okay. And of course, so we have the caching as well. The L1 cache, L2 cache, L3 cache in the upper side of the RAM. Okay. So when you go up, we need less storage, but getting faster and faster because it's getting closer to the processor and also the superiority of the technologies. Okay. And of course, the tertiary storage is pretty much backup. So therefore, we very rarely read it, but of course we have to write it in case of a disaster. But in case of an issue, only we read it. Okay. Right. You know what is primary storage or the memory, right? Remember, we have the static RAM and dynamic RAM. Static RAM is used in caching. Dynamic RAM is used in normal memory. So SRAM is faster. So that is why we have cache L1, L2, L3 cache. We have discussed the caching techniques. We always first look at the cache. If it is not in the cache, only we look at the cache, the next level cache, and then only we go to the memory. Okay. Right. So those things, anyway, you have learned. Right. So the dynamic RAM is your normal RAM. That is your bigger RAM. Okay. So then you have the secondary storage. So mostly these days, secondary storage is SSD, but still some people use the magnetic disk as well. Okay. Right. As I told you, so we measure registries in kilobytes, RAM in gigabytes, and of course, hard disk in terabytes and so on, right? So of course, you must know that 1024 byte is kilobyte, 1024 kilobyte is megabyte, 1024 to the power 10 megabyte is gigabyte, 1024 gigabyte is terabyte, because we have to do some calculations, okay, later on. Right. So the tertiary storage is pretty much the backup storage. Okay. So huge in size because we want to back up most of the time the entire database, right? Not half of the database. Right. So the flash memory, of course, the optical drives are there for tertiary storage. Still, some people use magnetic tapes, but it's very rare now. Okay. Right. So they have given you activities as usual. Categorize the following devices as primary, secondary, or tertiary storage media. So that you should be able to do. Right. Now remember, the main memory RAM and above are volatile. When you switch off the computer or main power supply is off, contents are lost. So therefore, we need to persist data, permanently save it. So we persist data in secondary storage. That is your SSD or hard disk mainly. And of course, we can persist in tertiary storage, but that is offline for backup. Okay. But we mainly persist in the secondary storage. So we can use SSD or we can use, so you have to read the additional things. I don't explain the additional things, right? Actually, it's too much details are given, but anyway, you can read it at least once. Right? I already explained we are interested in the physical database design because your data is saved in the secondary storage in data files and index file. So that is what we are looking at here, and we call that as physical database design. Right. So that is optimized for the database technology. And of course, physical layer is also there. Okay. Right. So when it comes to, remember in layer 2, conceptual layer, we look at the table as something like this. It has set of fields, then it has set of records or tuples. Right. So that is a logical view. That is not the reality. We have fields, we have records. When you insert a record, another record is added. That is purely a concept that we use to write SQL queries and so on. Okay. But in physical layer, actually what you have is a file. So this is a table or relation, and this is your physical layer file. It will have pretty much the same structure, but it can have slightly different structure also. Sometimes this table is related to multiple files. It has auxiliary index files and so on. The way you look at here is not the way the data records are actually saved and so on. So at logical level, we have table. Table consists of records and each record having fields. And in physical layer, we have a file or data file. And data file again have records. Right. Again having records, and each record consists of fields. Okay. So we use the same word record, but the way those arranged can be different. Okay. So when it comes to arranging your data or tables in files in physical layer, your database management system with the help of operating system. Remember, one of the key tasks of operating system is manage files. So what are the key tasks of operating system? OS. So one task is manage hardware, manage programs, so software for process management. Another task is file management. Another task is, of course, basic security. Hardware management, program management, that is managing your install, uninstall, upgrade as well as running process. And file management. So therefore, your database management system has to collaborate with your operating system when it comes to handling data in the files, because the DBMS doesn't get the direct access to files. always it is under the control of operating system. So therefore, your operating system also has to support certain file types. Okay. And that is why the performance also sometimes somewhat depends on the operating system. So that is why a lot of people prefer Linux operating system. Right. So what are the different type of files? In general, right? The operating systems allow and also DBMSs can facilitate. So we have heap files, sorted file, hash file, B-tree files, right? So we will be looking at mainly these three, but we will look at the B-tree files as well at the end. So what are the differences? So we take one by one, starting with heap files. Okay. So in heap file, we just enter the record to the end. So when there's a new record, we just add it to the end. There's no sorting order, nothing. We just keep adding to the end records. Okay, so that is called heap file. That is the simplest possible file, but the biggest disadvantage is that there's no sorting order. There's no other mechanism to access it. So then sorted files, it maintains the sorting order. Right. Maybe we have sorted according to the salary or department ID. It's always new records are added to the correct order, or correct location in the file, physical file. So that is called sorted file. Hash files use slightly different technique where I use a hashing functions to decide in which block your records are added. Maybe your first record is added to 10th block and next record is added to the 25th block based on the hash value. Right? B trees use a data structure called B tree or B plus tree data structure that we will look at later. Anyway, we will revisit one by one. So that is our subject basically. Right. So they have given some more activities. State whether the following statements are true or false. Okay. Right. So do this because we'll do the activities also because you don't have much past papers also for this subject. Right. Quickly do. These are anyway easy questions. Okay. But you do it first. I'll give 1 minute. Right. First one. The place of permanently storing database is primary storage. True or false? First one. False, right? So the primary storage is your RAM. You don't store it permanently. Permanently store it in the secondary storage, right? So that is false. A heap file has a specific ordering criterion where the new records are added at the end. Okay, so that is a very strange answer anyway. The new records are added to the end is correct. Okay, new records are added to the end. Heap file has a specific ordering criterion. What is that? Has a specific ordering criterion. No, there's no, I don't know whether adding to the last one is also ordering, but I don't know. This is a very confusing answer for me, but there's no specific ordering criterion. You just add the last one to the end. So therefore, I will say false, but it's a very fuzzy sort of a statement. Okay. Upon retrieval of data from a file, it needs to be found on the disk and copied to the main memory for processing. Yes, right. So it needs to be found on the disk, right? So then you have to copy it for the main memory because we process, you take data from memory. We don't take, the processor doesn't take data directly from your secondary storage. We will take it as true. Right? Say false, false, true. The database administrators need to be aware of the physical structuring of the database to identify whether they can be sold to a client. What is that? The database administrators need to be aware of the physical structuring of the database. That is correct. Of course, database administrators must know the physical structure. To identify whether they can be sold to client. I don't know. What is that? They can be sold to client. So why? What is mean by it's they can be sold to client? That is terrible English. Okay, I don't know what this statement is. Physical structuring of the database to identify whether they can be sold to a client. Yeah, maybe if you are a database administrator, right? So we must know the physical ordering also and possible maybe options so that we can market saying that you can improve the performance like this and that. But anyway, it's again a very fussy way. I can't understand what is mean by they can be sold. They can okay. They can be sold to a client. I think something wrong with English also. But anyway, I will take it to assume that what they mean by they is the database or the database management system. Okay. And anyway, it's a little bit, not little bit, heavily confusing English. Okay. Solid state drives are identified alternative for magnetic disks. Yes. Right. Anyway, the fourth one is I don't know what kind of English is that. Okay. So yeah, so that is also my answer also. Okay. Right. So next one. So I already explained you that. So when it comes to physical storage, I told you we have file consisting records, and each record can consist of fields. But in reality, each data is set of bits and bytes at the very low level. So therefore, if you look at the ultimate view, you have a set of bits, right? And of course, we can categorize set of bits as 1 byte. 8-bit is 1 byte and so on. And 1024 2 to the power 10 byte is kilobyte and so on, right? So therefore, we can finally we can say we need this much of byte of storage for this particular store in this particular record to store this particular table. Okay. Right. So when it comes to hard disks, okay, so your syllabus more concerned about the hard disk than SSD. You can visualize hard disk something like this. Right. So they ask question about these things as well, hard disk access time and so on, because we must aware of these things. So we know that hard disk has set of disks or array of disks. So disk 1, disk 2, disk 3, disk 4, disk 5. Right? And each disk has tracks. Right? Tracks like this. So that this is something you know from your O-level actually. Okay. Tracks. And then we can, the hard disk has this kind of a separation and it creates sectors. So these are the tracks, and this is a sector, this is a sector, this is a sector, and so on. Basically, your data is saved in those sectors. Okay. So therefore, and also every disk has those tracks and sectors. And then we have read-write head for each and every disk. Right? Each and every disk has read-write head. So these hard disk plates can be rotated. So they can be rotated. What you have to remember is they rotate in the same direction together. So they can't rotate independent. When this rotates, all the others are also rotating. That is how it is built. Okay. So first thing is when your program want to locate a particular record, it determines which sector that particular data is. Right. So that means which sector, maybe the third, this particular sector. Right. So we have the read-write head, and this is a fixed structure, and this can move this way and that way. This arm. Okay, arm can move laterally, but again, when this move this way, all the arms are moving that way. Right? When it goes So that means all the disks rotate together, all these arms laterally move together. Okay. And the first thing is your disk plates will rotate until the particular sector, right, comes under the arms. Okay, comes under the arms. Okay. Sorry, no. First thing is these arms laterally move until the relevant head comes under the particular track. So that is your first thing. So it either move this way, of course, all these are moving that way, or the other way until the read-write head comes under the particular track. So that is the first task. The second task is maybe your sector is somewhere here. So now it has to rotate so that it comes under the read-write head. So that is called rotational delay, right? So first this laterally move until it comes to the correct track. Then all these rotate until the particular sector comes under the read-write head. But only one particular sector is our requirement, but all these has to rotate. All these arms has to laterally move. All these disks has to rotate. And now our read-write head, or one of these read-write head, is right behind the correct sector. Now it can read the data. Okay, now it can read the data. Okay, so because these arms are moving together, these plates are rotating together, the storing of, so if a particular file has saved in this particular sector of set of files or set of records, if this is filled, what happens is it store the next record in another plate, another disk plate in the same corresponding sector. Because these things move together, then if this, after you read in this sector, if it is not there, without any rotation or lateral movement, it can read the corresponding sector in the other plate and corresponding sector in the other plate and so on. If all those corresponding sectors are filled or exhausted, then only it will do a rotational and save it in another next one. So that is how it works. And also again, when you rotate this, others are also rotating. So then it will say there, and so on. So therefore we can sort of visualize it as data is saved in a part of a cylinder, because your data is saved here, here, then here, and here also. So something like that. Because that is where you get the highest efficiency when it comes to the hard disk, the way hard disk operate. Okay, so that you have to understand. Okay, so therefore there are three components: the time taken for this arm to move, time taken for the rotation, and for the transfer time. So that is your total time of accessing a particular record. Okay, so then of course there can be subsequent rotations, subsequent arm movements, and so on. If it is looking at the next location and so on. Okay. Right. So the next thing is you have to understand how do we read a record in the file. Okay. How do we read a record in the file? Say when you write a select statement, say select all from employee where employee ID is say 108. So remember this record is in the file or hard disk or your storage. So when it comes to operating system, the smallest amount of data that it can access from the disk is called a block. Okay, block of data. So most of the time that block of data is same as a sector size. Sometimes it can be few sectors or it can be part of a sector. Definitely your operating system can't go and directly get a record. No, it doesn't have that kind of idea. But it can access a particular block of hard disk or block of your storage to the memory. It copies it to the memory. Okay. So then in the memory, look for that particular record. Maybe it has loaded 1,000 records or 300 records. Then it check whether that particular record you are looking for is in that particular block. You look at that in the memory. And if it is there, of course, it will be sent to the client, your PHP or Java or whatever. Or if you are writing a SQL prompt, it will be stored in your SQL prompt. That is how it works. So there's no way your operating system to read only a particular record. It has to always, the smallest unit it can access from the disk is a block of data. And it may be having more than one records, obviously, sometimes hundreds of records. So this is super important to understand. And what happens if you want to update? Again, say you have to upload the block containing that record to the memory. In the memory, you update that record, and then you have to write that entire block back to the storage. That is how you update a data record. Okay. And even when you delete, the same thing, you have to upload the particular block to the memory, delete that record, or mark for deletion or whatever, there are different techniques we do. Then you have to again write back that block to the storage. So therefore, you can see that for computer operating system level, it is read and write operations. If you retrieve data, only read operation, read in that particular block. But if it is update or delete, you have to read the block, do the updation, and write the block back. Delete is also sort of update, because you just delete that record, means update that block and write back. Or you mark that block particular record as deleted, mark for deletion and write it back. So therefore, for operating system, it is set of read and write operations. But retrieval is only read operation. You don't have to write back the block. But update and delete is read and write back the block. Always those things happens at block level. The smallest unit your operating system can load to your memory is block of data. So this is super important to understand the rest of the stuff, and also to understand the transaction handling we will be doing as the last topic in your syllabus. Okay. So sometimes we call it this block, sometimes we call it page as well, but the better word in storage, we say this block. When it comes to the memory, we say that this block is in our memory page. Okay. And this size of a disk block is usually fixed for that particular operating system and hard disk and so on. Okay. And there is each block can be identified using a hardware address. So those addresses are created during the formatting of a disk. Okay. So basically, all your select, insert, update, right, delete, those are all set of read and write things. But only select is need only reading a block, but insert, update, delete need writing. So then someone will ask, why do we need to do read and write back to both for insert? Because insert also, when you insert a record to the database, first you have to read the block that you want to insert the record to the memory. You read the block, maybe it is already having some record, you read the block to the memory, then you insert the new record to the block, and then you have to write it back. So therefore, even insert is read and write. Update is read and write. Delete is read and write, but select is only read. Because once you read that block, you can just discard that memory page, because you don't have to write it back. Okay. So if you have any questions, you need to ask. This is not easy. I'm not saying that this is super complicated, but this is not as straightforward as you just read it and understand straight away. Right? Of course, you can read it and understand. You have to spend a lot of time taking the big context, connecting these things here and there. Okay. Right. So there are different type of hard disk, like fixed hard disk, movable hard disk clusters, and so on. So we don't need to go into that details and look at how these different mechanisms work. But for you, only thing is you have to understand that we read a block of data to the memory, and if it is retrieved, you get it from the memory, or you just update the block and again write back in case of insert, update, and delete. Okay. Right. So you can do this one also. Map these words: capacity, track, buffer, hardware address of a block, cluster. Remember, cluster is collection of several shared blocks. That means those several blocks are considered as one logical block. So then we call it cluster. Okay. Do it. We'll do those as much as possible as well. And we want to finish about half of the topic today and finish the next half next day. So then 3 of your 5 topics are over. That means more than 50% of the syllabus is over. Okay, so it's super easy. Let's start with the easier one. The concentric. So concentric means same center. Okay, concentric circles on a disk where information is stored is called track. Of course, data is basically shared not in the track but in the sectors. But tracks are also related to that. Combination of cylinder number. Remember, we look at the data as saved in a cylinder because these these plates are moving together, the arms are moving together. So therefore, we can think of that data is saved in a cylinders, right? Because when data is saved here, the next is saved here, rather than then you don't have to do any movements. Okay. So combination of cylinder number, track number, and block number, right? We can call it the hardware address because we need all those things to uniquely identify a particular block of data. Okay, block of data. Number of bytes that disk can store, of course, that is the capacity of that disk. Collection of shared blocks are called clusters. Okay, cluster. This block stored in a reserved location in primary storage. So that is called buffer. So what is mean by buffer? Buffers are temporary storage locations, right? Buffers. So from buffer, we can write to the hard disk by operating system. The DBMS will write to the buffer. Operating system will, because operating system may be busy doing some other tasks, it will flush it to the hard disk. And also when it read, until your DBMS get the access, it will be in a buffer. Okay, reserve location in the primary storage or memory until that disk block is used. We call it the buffer area. Right, so that is pretty much how hard disks work. SSDs are more sophisticated devices, okay, or the flash storage. You know that in SSD, another name is solid state device. So there are no moving parts, right? So that is why SSDs are stable. Hard disks get crashed because there are movements, mechanical movements. And if there's a dust particle, even a dust particle can crash it. And there can be bad sectors and so on. But solid state devices are 100% electronic storage. Basically, it contains NAND gates or NOR gates, right? So therefore, it is much faster and also much compact, right? And also the way we access data Of course, still we have to access it as blocks, but it has less complications than hard disk. Okay. Yeah, you have to read these things, right? So state 4 key features of a solid state drive. So you can write something like no moving parts. It's consisting of logic gates rather than magnetism. It's more reliable, right? Faster, right? So you can find out some proper points from your note itself also, okay? And also the addresses can be directly accessed, right? Data is less likely to fragmented because we can access any place and quickly change those locations, okay? And also it's more expensive right now. Right, so now let's look at how we can physically store data in files, right? Physically store data in files. So far what we discuss is basically the hardware devices like hard disk and SSD. And remember, we have set of, this is logical level, we have a table or some table or relation, and your relation has set of records or tuples, and you can visualize a table as set of fields as well. Okay, so therefore each record also has the field values. Okay. So that is logical view, conceptual view. Okay. And when we design our database, usually we decide the data type as well, whether it's integer, varchar, if varchar, what is the bit, varchar 200, varchar 50, or maybe date or date time or decimal. Decimal also we can decide the width, how many decimal places, what is the width of the whole number parts and so on. Okay. So we have data types. And we know that data type can determine the required storage. Right. So this is how you create a table that you know. Right. Do this also quickly. 30 seconds. Select the data type that best matches the description out of the following. Right. NIC number of Sri Lankans. Of course, the NIC number can have characters and so on. Therefore, we can't go for numbers. Right. Of course, character is there. Right. Integer, Boolean, floating point, date time, Boolean. So we have to go for character. For character or what variable character. Or we can go for fixed character also because NIC number is a fixed length. So there's something called variable character, fixed character. Of course, here just there's a character. But if we have fixed character, we can even go for fixed character also. Okay. The access time of users for the Ministry of Health website within a week. It's access time of users. Okay. Access time of users for the, I don't know what is the access time. Is it millisecond or exact time that person access the website? The access time, maybe the time the user has access to the website, right? Again, it is not very clear. If it is the time that the particular user has accessed the website, we have to go for date and time. Okay, date and time. The number of students in the class integer because it can't be decimal. Cash balance of a bank account, it can be decimal also. From available things, we have to go for floating point. Responses to the question by a set of students whether they have received the vaccination of rubella. Obviously, it is Boolean. Okay. Right, so let's move on. Right. So placing file record on a disk. Now we are into the physical storage organization. So at physical level, we call it file, not table. Okay. So in a file, we have again set of records. Right. Of course, file you don't have to look at like this. File you can even look at it something like one record, next record, next record. So that is how usually we look at a file. So this is how you look at a table. You look at a file as record, next record, next record, next record, next record, and so on. Okay. And this is my record 1, record 2, record 3, and so on. And there are two possibilities. One possibility is each record has the fixed length. If it is 10 byte, each record has 10 byte. So that is called fixed length record. The second option is we can go for variable length record. In that case, maybe this is 5 byte and this is 3 byte. And maybe this is 6 byte and again 5 byte and so on. So those are called variable length record. So variable length record means, for example, say for a particular record, the user has not added, say, phone number. So then we shrink that part. We skip that part. So therefore our length, we use lesser storage because that particular record, there's no phone number or maybe not email number. So then it is, you don't need 6 kilobyte, maybe not 6 byte, just 5 byte is enough. But in fixed length records, even though say phone number is not given for the, or null, we allocate that length. So therefore always we get the same length for each and every record. So that is the difference between fixed length record and variable length record. Each approach has its own pros and cons. Obviously, if you have the variable length record, it is more storage efficient. We need less storage because we don't waste our storage. But when it comes to accessing, handling the records, it is more complicated because we can't, for example, if a particular block has 1,000 records, if it is fixed length, and if you know that this is the 800 record, we can calculate and straight away go there because we know that every record is fixed with, right? So straight away we can, in the memory, we can access it. Of course, in the memory, we know that at this particular offset, this record is there because every record has a fixed length. But if it is variable length, because they are of different size, we have no such way to go do it. So we have to sequentially go from one record to the other until we get to the correct record. So therefore, when you access a particular record in the block, in the memory, fixed width is better, more efficient. Variable length is less efficient because we have to go by record. Okay. So therefore, it's a decision we have to take whether to go for fixed length or variable length. It's a decision based on whether we think about the storage or we think about the efficiency of searching in the memory. Okay. And also when we have optional fields, more optional fields, right? So maybe variable length is a little bit better option because we will be wasting a lot of storage otherwise. So likewise, we have to take those decisions. But if you have only few optional fields, right? So then fixed width is better. But if you have a lot of optional fields, it can waste a lot of storage if you go for fixed length. Okay, so those are the things we have to consider when deciding whether to go for fixed width records or variable length records. Okay, and also you may have the mixed approaches as well in certain cases. Okay, and also there are some special cases we have to think. In fixed length record, what happens when you want to delete a record? Because we calculate based on the offset. So sometimes if it is a fixed length record, when we delete, we just have to mark it as deleted rather than deleting it. But variable length record, again, if you want, you can mark it as delete, but most of the time we can reorganize. Because we don't do that kind of offset calculations to find the record. So when we do the offset calculations, sometimes rearranging will ruin it. Okay, and things like that also we have to consider, depending on whether it's a fixed length or variable length. How do we delete records, right, and so on. Right. So in variable length record structure, how do you know that the end of a record? In fixed width, we know that after 5 bytes, say this is the next record. Maybe next 5 bytes is next record. So therefore, you don't need a special mechanism because it's a fixed width. But in variable length, it's different width. So therefore, we need at the end of a record, we need a special marker character. So that marker character specify that, okay, that's the end of this record. Now we are starting the next record. So then again, the marker character is there. So that is how the variable length records identify the end of a record, which is super important because when you are searching also, we have to go by record by record. We can't just calculate the offset and directly access a record. Okay. So you have to understand these things together. So these things are interrelated. Okay. And later we'll look at the indexing and so on. Again, we will talk whether it's a fixed length record or variable length record and so on. Okay. Right. So this is a fixed length record. Right. You can see every record has the same sort of a length. Right. Of course, this is not the same record. This is one record. The name, NIC, department, job code, and so on. So the next record is also going to have the same length. Right. In this case, it is one record is 44 byte, right? 38 plus, sorry, I don't know. This is not 44 byte anyway. Yeah, so total length is 44 byte. Okay, the total length is 44 byte. Then the next record is also taking 44 byte. Next record is also taking 44 byte. Okay. And also we know the second field, third field also by width. So that is another advantage. So if I am looking for the department, I know that exactly where to come. Okay, because all are fixed width. But if you want, still you can have the separator, but separator is really needed. It's a must only when it is variable length. Okay, variable length. But if you want in fixed width also, you can have a separator. And sometimes you can have separator for the fields also. Fields also. But again, it is not a must. If your fields have fixed width, again, it's optional thing because you don't need a separator because you know that first byte is your primary key, second byte is 2 byte is salary and so on. But if you want, you can have a separator for the fields plus separator for the record. Of course, then the record separator must be different from field separator. Okay. But having these separators in variable length files is a must. In fixed width file, it is optional. Okay, it's optional or usually you don't need it. Okay. And when you have so many optional fields, right? Sometimes what we can do is, because sometimes you will have either this field or that field. So then you can have something like field name and field value also. Right? Field name and field value. Just to make it specific. Okay. So those are possibilities. It doesn't mean that we always use these things. Right? Say we have 5 fields, usually we get data for one of the fields. So then rather than wasting allocating 5 storage locations in your file, if you know that only one will be there, we can just allocate one particular storage unit and we have the store data, field name and field value. Right? So it is more efficient. So likewise, if there are so many optional fields and only 1 or 2 is stored, we get the data, we can go for field name, field value, special approach as well. Usually you don't go for field name, field value. We use the separator or the with. But when we have so many optional and only 1 or 2 is we are getting the data, we can go for field name, field value as a better performance option. Okay. And there can be a situation where we have repeating field. That means that field is or value is repeated. But anyway, that is a terrible thing to do because then it is not atomic. It's not in first normal form. But maybe a legacy database or something. A particular field, you can have multiple data, like multiple uh, phone numbers. But again, I'm telling you, this is a bad thing in the design, but maybe a legacy database. So then you can use some sort of another separator to identify this is the end of the first value, and now we are into the second value and so on. So that means you can have the file record separator, field separator. You can have even separator for values in the same field as well. But that is if you have repeating value for one field. But anyway, that is very rare because that is your table is not in the normal form, right? First normal form. But you must know possible problems and solutions because we are concerned about the physical structure, not optimizing in the logical level. Right. So we'll take a break. We'll be starting at say now 9:05. 9:20. So do this exercise also. Okay. We'll do the exercise and then move on. Okay, so let's continue. Right, the file where the size of records in it are different in size is called variable length, right? File where the size of a record in it are different in size, yes, variable length file or variable length record file. Includes different type of records inside it. Different types of records. What is that? different types of records inside it. What is the best one? Maybe variable field record. So you can have variable field. Okay. So different type of records means yes, variable field file. Okay, record file. In a file, the records belong to record type. What is that? In a file, the records belong to I'm not very sure. So just double check whether they have given a specific name. Okay. A length record can be made by assigning null for optional fields where the data values are not available. Null for optional fields. So maybe fixed it, right? So we have to at least say there's a value. Value is null because we can't skip it. You can see by assigning null for optional fields where data values are not available. Because it's a fixed length, still we have to mark it. We have to take that width. Okay, but there's no value there. So therefore we have to say it's a null value. To determine the terminate variable length special characters name as can be used. We call it marker character, right? Marker character. Okay. So terminator character. So this is this. Okay. So we can call it the separator character. So there are different names people use. I think the word they use in your note is separator character. It's separator character. So these are also separator, but field separator character. Right. So this is your separate of the record or terminate character. Different words are used. Okay. Right. So let's move on. So now we move on to some calculations as well. The disk storage and basic file structure. Right. So I told you that we save data in your disk in blocks. So this is the smallest unit your operating system can load it to memory or load it to a memory page. So therefore this block has a size in bytes, and also this block can have multiple records. Okay. And of course each block has a block address which your operating system has the access to. Okay. So when your database is looking for a particular record, with the help of the operating system, it has to find out what is the corresponding block. Then load that block to the memory, and from that block in the memory, it can identify the record. For retrieve, insert, update, delete. Remember, even for insert, you have to find the next available block or the block that you want to insert the record. Right? So block is unit of data transfer between disk and memory. Okay. A block can keep multiple records. So number of records that you can save in a particular block is called block factor, VFR. Okay. For example, if your block is 100 byte, and if each record is 5 byte, obviously the block factor is 100 byte divided by 5 byte. So that means you can keep 20 records in a block. So therefore block factor is the block size divided by record size. Block size divided by record size. Let's assume record size is fixed. Right? Because if it is a variable length, the different records have different size. So all your questions, unless they mention, you can assume that they are talking about fixed length records. Fixed length records. And also there's a small issue. Now, for example, this is perfectly divisible, 100 divided by 5. But what about if my block size is 100 byte, but my record size is, say, 8 byte. Now, I have 100 byte block, one record take 8 byte. Now, this is not perfectly divisible. So, this is basically 100 divided by 8, 1, 8, 20, 2, 16, then 4 remains, that is 12.5. So, if you take something like 12.5 or even 12.1, you have to floor it, because you can't keep 0.5 of a record in a block. In general, you can't keep part of the record in a block. So therefore, if you get something like the block factor is 12.9, right, you have to say it's only 12 records can be put it in one block. Always you have to floor it, right? Because we don't keep 0.9 of the record, we just keep that we just take that record to the next block. Okay, so whenever you calculate the block factor, unless they talk about variable length records, and also there's something for span and unspanned, which we look at in next slide, you can always floor it. You can always floor it, because usually we don't keep part of the record in this block and other part in the other block. Okay, because it's small waste of storage, but otherwise to access that record you have to access two blocks, which is more time consuming performance it. Okay, so make it flow when you calculate the block factor. What is block factor? Number of records that you can keep in a block. It depends on your record size, and also it depends on the block size of the computer or hard disk. Okay, so therefore sometimes there will be some space available, but we can't use it because it is less than the size of a particular record. So therefore there can be some wasted space, and that is, remember, your block factor into number of records is your storage use, and this is your block size. So therefore block size minus block factor into number of records is your unused space. Okay, right now. Okay, maybe we can keep 100 records in a block, but we have used keep only 30 records. So that means the unused space is the total space of the block minus block factor into number of records we have saved. And when we fill the entire records also, again small number of bytes will be remaining, because that space cannot be used, because it is less than that space available is less than space of one record. Okay, right, I hope you understand. Okay, so B is the block size, block factor is number of records in a block. So number of records in a block, that is your block factor into, sorry, not number of record, the block factor is, number of records in a block into the record size, that is the total space you use. So therefore when you subtract that, you get that the space that we can't use, the wasted space. Okay, because that is not fit into a lesser than the space of a record. Okay, right. So that is when we use unspan approach. Unspan means one record is never allowed to go into multiple blocks. Okay, so one record must stay in one block. But if you go for span organization, then that small wasted area can also be used. Right? So because in span option or strategy, a record can be in multiple blocks also. So therefore, when we have a small available space here, maybe my one record is 10 byte, but here we have another 3 bytes. So we can put part of that record here and the other part in the another block. So then we call it spanned organization. But in your calculations, usually you can assume that we go for unspanned. We don't allow a record to go into multiple blocks. And in unspanned organization is where we do the flooring, because we assume that there's nothing, we don't keep say 75.8 records, because then that 0.8 we can't save, we just take it to the other one. Okay. Right. So this is again explaining the unspanned versus spanned. In unspanned, if the space is not enough to keep a record, we just keep it. And that is the calculation we did. So this space, wasted space, is the size of a block minus VFR into number of records that fit into this. Because this is always this much of a space is wasted, because it's unspanned. But if it is go for spanned organization, this storage also can be used to keep, maybe this is the part of the fourth record, this is the next part of the fourth record. So therefore we use it full. This is just the pointer. Point into the next block. Because the rest of the record 4 is here. So then you don't waste it. But anyway, that waste is very small. So therefore, unless they talk about it, you can always assume we use unspanned file organization, record organization. Okay. So that is the difference between span versus unspanned. Right. Now let's calculate. Now we know what is block factor. Block factor is number of records fit into a particular block. And in unspanned structure, that is our default structure, you have to floor it, because we can't keep half or part of the record. Okay. So now we can calculate number of blocks needed to store a file. Number of blocks in the disk needed to store a particular data file. So that is called B. So B is number of records in the file, assume fixed width, right, divided by block factor. Because block factor is number of records in a block. So if you can have only 10 records in a block, and if I have 50 records, so number of blocks needed is 50 records divided by, say, block factor is say 10, that is 10 records per block. So then I need 5 blocks. But again, here also you can get a decimal value, right? For example, I have 60 records. My block factor is maybe 12, or my number of records is 55. Block factor is 10. So that means I can keep 10 records in a block, and I have 55 blocks. So then what is the number of blocks needed? So then it is not 5.5, because there's nothing called 5.5 blocks, right? So then it is 6 blocks, right? 6 blocks, that is 5 block is not enough. The final block we are not using the entire block, but number of blocks needed is you have to ceiling it and say 6 blocks. So that I hope you can understand, right? So we can't say I need 1.5 block. We just say I need 2 blocks. Of course, that second block, we are using only part of it. We can further store it, but right now we are using this number of blocks, right? So the block factor is number of records per block. Okay, so that is block size divided by record size, but you have to floor it because unspanned. The number of blocks needed is number of records divided by block factor. There you have to ceiling it. Because if I say I need 1.2 blocks, we just said we need 2 blocks. Okay, so these are not difficult things, right? Very simple calculations, but things will be more and more complicated when we go into the indexing, right? Multi-level indexing. So therefore, it's super important that you understand these things properly. So this is still we are not into the complex area. Still we are in the very simple area. Okay, but you have to perfectly understand this side because understanding the especially multi-level indexing is super challenging. But there also we use the same concept. So therefore, if you have any question, doubt here, you have to ask it and clarify it. Okay. Right. So this is an example. Right. So now we can do this kind of exercises. There is a disk with block size 256 bytes. So that means your hard disk has a block size of 256. Each block is 256 bytes. So this is again 256. The file has 50,000 records. So the number of records as a logic is 50,000. Okay. And it's fixed length. So usually you can always assume fixed length unless they mention, right? Usually they give only fixed length questions. Each record has following fields. Name take 55 bytes. The degree take 2 bytes. Sex take 1 byte. Student ID take 4 bytes. Phone take 10 bytes. Now you can calculate one record length. So one record length is 55 plus 4 plus 2 plus 10 plus 1. That is 72 bytes. So that means one record is 72 bytes and it's a fixed fee. Okay, fixed fee. And we have 50,000 records like that. So now you can, if you want, you can calculate the total size as a concept. Okay. Right. So now we want to calculate the block factor. What is block factor? Number of records in a block. So number of records in a block is, the block size is 256 bytes. One record takes 72 bytes. So therefore block factor is 256 divided by 72. If it is not perfectly divisible, you have to floor it. Not ceiling, you have to floor it because you can't keep half of part of the, you can assume that it is unspanned. They have not mentioned, but you can assume that it is unspanned. So therefore, block size is 256 divided by 72. And I think this one is perfectly divisible as 3 records. Is it? Let's say 72 into 3, 260. No, right? It's 3 point something, right? Of course, we can't keep 3 point something. So therefore, we have to take it as 3 records because we have to floor it. We have to floor it. Okay. So therefore, one block can keep only 3 records. In this case, those are big records. Therefore, one particular block can keep only 3 records and there's a waste of storage. Now, if you want, you can calculate the waste of storage for each and every block also. That is 256 minus 3 into 72. Because one record is 72, right? So what is 72 into 3? 216. So each block, there's a waste of 256 minus 216. That is 0. Each block 40 byte is wasted. Right? Each block 40 byte of data is byte storage is wasted. But we can't help because we go for unspanned. So unless they mention, you can always assume it is unspanned fixed width. Okay. So now we know that we can keep only 3 records in a block. And now you can calculate number of blocks needed. Right. So that is total number of records divided by block factor. Total number of records is 50,000. So one block can keep only 3. So therefore 50,000 divided by 3. Right. 50,000 divided by 3. Now you are ceiling. Because if you get something like 100.2, that means you need 101 block. So you have to ceiling it also. So you divide it by 3 because one block can keep only 3 records. Then you ceiling it. This is the number of blocks needed in this case. 16,667 blocks. Okay. So it's not difficult question, but just remember to do the ceiling, flooring properly and keep track of your assumptions. We assume that it's a fixed width and also unspanned. And they can even ask you what is the, in each block, what is the waste of storage. That also you can calculate. Okay. Any questions? So this is our assumption we did. Fixed length, unspanned. Unspanned means a record cannot be into two blocks. Okay. Right. So this is another example. So quickly do this exercise because we have to do exercises because this is where the students are really struggling. Right. Similar question, but do the calculation. Answer is not given, but you have to do it quickly. Right, let's do it. So the block size is 512. One block is 512. The file has 30,000 records. Right, 30,000 records. Of employee records of fixed length. Each record has the following fields. So that means you have to calculate the one size of one record, that is 30 plus 9 plus 9 plus 40. Right, so let's add it. 39, sorry, 9 plus 9 is 18. 18 plus 9 is 27. 27 plus 8 is 35, 36, 40, 44, right, 44. Then we have another 40 here, 84. Okay. So one record is 84 byte. Just double check whether I made a mistake. 84 byte. Blocking factor is number of records per block. That is 512 divided by 84. Right? 512 divided by 84. Remember, we have to floor it. I will be using the calculator. $115. Oh. Let's do it again. Say 30, 40, 70. So that is 70. Then we have 9, 9, 9, 27. 27 and another 9. 36, 40, 44. 44, right? Is it? Yeah, 114. 114, okay? So, sorry, 114, yes. 114 byte. So, therefore, so the one record is 114 byte. 114 byte. So, therefore, block factor is 512 divided by 114, but we have to floor it. Okay, floor it. Sorry, that I didn't get it. Yeah. An additional byte is used as deletion marker. Yes. So that is something you have to understand. Yeah, I completely miss it. Yeah. So therefore, we need one more byte because there's additional marker that mark whether it's a deleted one or active one. So therefore, it's not 114, it is 115. Yes. Sorry for that. Okay. Right. So then the block factor is 512 divided by 115. I will be using the calculator. 512 divided by 115. That is 4.45. So that means we can keep only 4 records in a block. Remember, we have to floor it. So block factor is 4. Right? Block factor is 4. Record size is 115. Okay. Byte. Right. So calculate the number of file blocks required to store employee records assuming an unspanned organization. So now we can calculate the number of blocks. That is, the total number of records is 30,000. And we can keep only 4 records in a block. Right? That is block factor. So therefore, number of records that number of blocks needed is, I think this is perfectly divisible. 2 and 15,000. That is 7,500 blocks. So you don't have to seeding it because it's perfectly divisible. But you have to seeding it, but it's perfectly divisible. So you need 7,500 blocks for keeping this particular file. Okay. Right. Right, so let's move on. Right. So remember, we have two type of operations. Of course, we have insert, update, delete, right? Insert, update, delete, and retrieval. But when it comes to file operations, it is just read and write. Read and write. Okay. So your select is a retrieval operation. You only have to read, but your update, insert, delete, right? Insertion, deletion, and modifications or updations, they need read and write. So therefore, they are commonly update operations. Even insert is update operation because we have to update a block. Deletion is also we have to update a block. And obviously update is again update a block. So therefore, we can look at it as retrieval and update, where retrieval needs only block read to the memory. Updates, that is insert, delete, modification, need both read and write. Okay. So understand this properly. Right. And also, sometimes our retrieval involves only one record. Right? One record. Say you want to select all from employee where employee ID equal 5. So usually one record can fit into one block always. So therefore, in that kind of a situation, we just have to retrieve only one block. And even update also. Update, usually insert, you need only one block because that block is in that block, you can save it in that block. So therefore, inserting a record, retrieving one record, and also updating one record. That update is filtering into one record. So there we need only one block to be loaded to the memory. And of course, if it is insert or delete or update, you have to write it back. And if it is just a select statement, just only read it. But there are situations where you need to retrieve multiple records, right? So this one is a simple selection where one block is enough. One block is loaded. But if it is something like salary greater than 60,000 and so on, so these records will be here and there. Here and there. So sometimes we may have to load 5 blocks, 6 blocks, and sometimes all the blocks for that particular file need to be loaded to the memory. And if it is retrieval, you just have to load it. Sometimes if it is update, you update effect multiple records. Maybe those records are in 10 different blocks. So then all those blocks we have to retrieve and modify and again write back. Okay. So therefore, we have to think about this when we design our database, because there can be performance issues when we load multiple blocks. Of course, there are situations we have no other option. Okay. But this is something we have to aware, right? Whether we have to retrieve only, read only one block or multiple blocks. But definitely for insert, right? We need only one block to upload. But even when you delete also, sometimes you delete multiple records. So delete from employee where salaries say greater than this. So then multiple deletions. So that means you have to load multiple blocks and delete that and write it back. Okay. Sometimes even insert, maybe you are inserting multiple records. Okay. So that is a different story. So then again, sometimes if it is sorted, data is sorted, then sometimes you have to load multiple blocks. Okay. Right. So these are some file operations. Open a file, right? Find a record. So when you read, now the other thing is when you open a file, you may be retrieving files. So you to keep track of what is our current location, we use something called file locator. So this is the current record we have read. Sometimes we have to reset it because that means again we want to do the searching from beginning, right? And obviously we have to close the file. So these are the file operations, right? You learn these things in Java, file handling in Java. Okay. Then of course you can read that particular record. Maybe you can delete a particular record, or you can go to the next and so on. Okay. Maybe you can modify that particular record, insert a record, and file and close it. So those are file operations, right? So these are not disk operations. Those are file operations supported by languages like Java, C, and remember the DBMS file. Ultimately, those file operations are done by programming languages, though it is not visible to us. For example, your Oracle database management system, the backend is pretty much Java and C. So therefore, internally, those file operations are happening. Okay. Open the file, locate a record, delete that one, close the file, and so on. And these are some more operations like scanning and so on. Okay, find all, find, order, reorganize. So don't worry too much about those things. We don't go into those levels because those are handled by your operating system. But just be aware that those are some file operations supported by low-level programming languages. Right. So when it comes to file operations, so we have to understand two main things. That is file organization, how the file is organized, and how are we going to access the file or the records. Of course, these two are related, interrelated. The way the file is organized determines the access methods. So for some file organization, some access methods are not available, right? And for some other file organization, so if you need a particular access method, you have to check whether that file organization support it. Okay, so therefore we have to think about these two together. File organization is the way files data is organized. Access method is how we access it. Okay, how we access it. Right, so this is another classification. Static file means we write to it, but very rarely we update it or delete it or modify it. So then we say it's a static file. Right? For example, when you install a software, maybe that file is also part of it, DLL file. But afterwards, almost we don't change that at all. It's a static file. But there are some files we have to insert, update, delete, or modify the file frequently. So then we say dynamic file. And if there's no way you update it or change it, that means not even rarely we change it, we call it read-only file. And if you want, you can make it read-only also for security purposes. Okay. Right. So this one you can do because this is file-related things. Okay. What is find, reset, close, scan, find all, and so on. Okay. Right. So now we are moving to another very important area. The file structures for different type of files. Different type of files. So there we will look at the heap files, ordered files, and so on. Okay. So the first type of files that we look at is called heap file. Heap file. Or we can call it unordered file. So unordered file means there is no specific order. Usually what we do is when there's a new record, we just add it to the end. Another record, add it to the end. So we don't care about any order. Right? Any order. We just add it to the end. So sometimes there can be multiple users write into this file. Even we don't care. Maybe this user enter record, this user enter record, again this user enter record, this user enter record. We just add it to the end. Okay, so then we say it's a heap file. Heap file is the simplest type of file to manage because we just have to add it to the end. Especially insert operation is super simple. And you don't need any extra structures to manage the file. Because we just add it to the end. It's something like our dara godak gahana wage. Udata දානවා. මේකේ නාකට දානවා. But this is the least efficient when it comes to retrieval, update, delete. The best efficiency for insert, because we don't care any other mechanisms. So therefore insert is super fast, but all the other operations are, this structure has the least performance. Unless you again read it in the same order as we insert. Of course, then it is not a big issue, but all the other places, searching a particular record, because even when you update, delete, you have to search it. There's no specific mechanism to locate a record. Only thing is you have to find the record one by one. For we say we have to do a linear search. Right? So we have no other option but to do a linear search. Linear search means you have to search from top one by one because there's no order at all. So therefore, definitely update, delete, modifications are super slow. Only thing is insert is super fast. Okay. Inserting a new record is quick and efficient, but all the other operations are fairly slow. Right. So therefore, now these are important for exams also. The average searching time is, right? If you have B number of blocks are used to keep the file. Okay, say 1, 2, 3, 4. So your file is kept in 4 blocks. Say 1, 2, 3, 4. And there's no order. We just have to search it from first record to the last record, right? So best case, maybe you find it in the first block. Worst case, you find it in the last block. So if you look at the worst case scenario, if you have B number of blocks, you may have to access all B number of blocks. That is the worst case performance. That means if you have 100 blocks, maybe you look at the first block, second block, third block, and unfortunately the record was in the 100th block, last block. So the worst case performance on the number of blocks access needed is B. Of course, the best case 1, that is when you get the first block, the data is there. But what about the average case? Average case is therefore B by 2. Because it's not just one search. If you keep on doing search, sometimes you get it in the second block, sometimes you get it in the 40th block, sometimes you get it in the 80th block. Say 100 blocks are there. So therefore, on average, we can say it's not always, but on average, it is B by 2. If you have 100 blocks, on average, you need to access 50 blocks. Because you don't go to the second block. You first search the first block and then search the second block. If you find it in the 80th block, you have access 80 blocks. If you find it in the 10th block, you have access 10 blocks. If you find it in the 50th block, you have access 50 blocks. So therefore, on average, average number of blocks needed is B by 2. Okay, so that you can understand because there's no other mechanism to identify which block your data is, your record is. Okay? So therefore, this is not very efficient for search, update, delete, because in update, delete also first you have to find the record. Okay. Remember, deleting a record is, again, you have to find the record. So that means again, on average, B by 2 number of blocks you need to access. Okay. So in some cases, when you delete, what we do is we just mark it. Because otherwise, we have to reorganize the files. Right? Reorganize the files. So rather than reorganizing your records, you just mark it, say, mark and say, this is just deleted. Okay. This record is deleted. And in some cases, this storage can be used for a new record, but usually heap files, we just add it to the end. So therefore, usually that marker record is, that space is wasted. Okay, so that is fine because usually we don't look for the marker areas and insert it because in heap file, we always insert to the end. Okay. You can see using the space of deleted record to store data can also be used, right? But it includes additional work. So therefore, usually you have two options. That is, when new record is inserted, you go and see whether there are marker areas and insert it, or you just always insert it to the end. The generally what happens is you always insert it to the end rather than you look for the mark areas, because then it is additional work. Because the idea behind heap file is just add it to the end. Okay, just add it to the end. But you have to think about these special cases. If the examiner asks, you have to say yes, this possibility is there. But it creates additional complexity for your heap file. Okay. So another option is periodically, right? Rather than when you are inserting a record, you look for the mark areas, maybe periodically, batch-wise, your file is reorganized. So those mark areas are used up by other records or reorganized. That is usually done periodically. Okay. It's something like defragmentation of the file. Okay. Right. So when you modify a record, again, that headache is there because you have to find the record and there's no way to find the record. So therefore, you have to do the linear search. So therefore, again, you have to have average B divided by 2 number of block you may have to access. Because you get the first block can search, then second block can search, third block can search, and maybe you found it in the 70th block. Okay. And then you update that record and save that block. Then you are done. But you can see on average B by 2 blocks need to be accessed. Right. In some cases, if you need to do a lot of searches, you can keep the heap file and another copy, separate file, which is sorted. So that means you are doing the insertion to the heap file, but you have a separate file, maybe periodically, you are updating those values into the sorted file, but that is overhead. It is not a typical solution, but anyway, they have mentioned it. But that is very rarely done because then you have two files. Right? So there are better ways of doing that rather than having two files, one heap file and another sorted file. So the better approach is keep your file sorted for user index file. Okay, so therefore this is not a good solution, but anyway, they have mentioned it as well. Okay. Right, so now we move on to the sorted files. Okay, sorted files or ordered files. So that means we don't just add the record to the end. We always keep a sorting order in the file. So that means we insert the record to a proper sorted location. We don't just add it to we access the last block of the file and insert it. No, we just access the relevant block and add it to the relevant location because we want to maintain the sorted order of the records. Okay. So which speed up, update, delete, and search, especially searching individual records. But it definitely slow down the insert because we have to insert it to the relevant block. Relevant block. So why it is speeding up the update, delete, and search of individual records? Because now we can do binary search. So you will learn the difference between linear search and binary search in our data structures and algorithms. So the searching and sorting is your final topic. Okay. So linear search means you just learn search one by one because there's no sorting order. There's no other option. So you just search. in worst case, sometimes what you are looking for is at the last one. Can't tell. But if your data is in sorted order, like 10, 12, 15, 30, 40, 45, 80, 85, 90, 95. So rather than doing linearly one by one, you can go to the middle and say you are looking for something like, say 30. So you can go to the middle and see which one is that. Maybe that is 45. So then you know that because it's sorted, you know that your data is in the first half. You can now forget about the second half. Then you go to the middle of that and maybe 15. Now you are looking for 30. So 30 is bigger. Now you know that your data is not in this part. So every time you do a lookup, half of the existing records you can forget about, because you know that my data is in the other half because data is sorted. And then again you go to the middle and you find that yes, that is what you are looking for. Likewise, you have to do few things, right? When you have say 1,000 records, you don't have to look at do 1,000 cases, right? Maybe within 10 searches you get it the record, or you find that the record is not there. If it is not there, when you have no other records to make it to half, that means what you are looking for is not there. So that is fine. So that means it's something that you are not looking for is not in the table or file. But this is much faster, right? So we say that linear search, the worst case performance is n, or when you have n number of records, the worst case n, average case n by 2. But if you do linear search, if you have n number of records, the average case is, sorry, even the worst case is log 2n, which is super. Right? For example, assume we have 1,024 records or blocks. Forget about the blocks. Assume we have 1,024 records. So worst case, if you have to do the linear search in a heap file, the worst case is I found it at the 1,024 search, because I am looking at the first one, second one, third one, fourth one. Right? But if I do a binary search, because it is sorted, I get the result in worst case also log 2024. And you know that log 2024 is log 2 to the power 10, that is 10. So that means even worst case, in the 10th access, I get the result. That means before 10th access, I get the result. Worst case, I get the result in 10th access. So after 10th access, I know that the record is not there. Now look at 1,024 versus 10. So this is, I have to worst case access 1,024, average case 512. But here the worst case also 10. Worst case also within 10 search, I can say whether the data is not there. The worst case is data is not there. So you can see how much speed up when the data is sorted. So this is sort of 100 times faster than linear search. 100 times. So that is the advantage of having sorted files. When we search on that sorted field, we can do the binary search, and binary search is far faster when we have more and more data. So this is 100 times faster when you have 1,024. When you have millions of data, it is not 100 times faster. It is, right, sometimes million times faster, because that efficiency increase exponentially. For less data, sorted file has less advantage, but for very large numbers, that advantage you can find compared to linear search, you will find that that is superb. Okay. That is why we prefer sorted file. So if anyone asks what is the advantage of having sorted file, we can do a binary search, which reduce the number of block access. Not by 1 or 2, right? Sometimes by 1,000 times. So where you have to do 1,000 access, here we have to do only maybe 10 access, and we get the data. Okay. Because accessing a block is very costly. You have to go to the file. File accessing is very slow, right? Accessing memory is fast. Accessing disk or SSD and copy to the memory is very slow operation, one of the bottleneck. So therefore, we try to minimize the number of block access. Okay, right. So in sorted files, we first have to identify a field because we can't sort a record file by more than one field. So we have to identify whether we want to sort it under your employee number or department number or salary, and then sort it. Then store it in that order. So that is what is mean by ordered or sorted file. Okay. So we don't have to do a sorting because it's already sorted. Its sorted order is preserved in storing. Okay. And also, if you are looking for something like 1000 and 1001 record, we can assume that 1001 record is also in the same block because data is sorted. And it's good for range changes also, range checks also. Sometimes we looking for something between, say it's ordered by marks. Say you are looking for students who have got marks 40 to 50. So most of the time, all those records are in consecutive blocks because if you have sorted by marks, if you are looking for employees of the same department, most of the time, all those employees are in consecutive blocks. Not all, almost all the time, they are in consecutive blocks. Okay, so it's good for range changes, range checks as well, range searches as well. Individual record is the result, still it is okay. If it is range of data that we are going to get as a result, that is even better. Okay, because most of the time all your data is in one or two block. If it is not sorted, sometimes you have to access all the blocks, all 1000 blocks, because they are spread across. Okay. Right. So that is the advantage of having sorted file. But remember, we can sort only for one field. So if you sort it for salary, now you lose your sorting for the employee number. If you sort it for the department number, now you have lost the sorting for the salary or employee number. So therefore, you can sort a file by one field only. Right. So now we move on to the hashing. Right. Hashing tech or hash files or use of hash techniques to locate a block. Still, you save it in blocks, but we use hashing techniques to identify which block this particular record is. Okay. Right. So we'll take a break. After the break, we'll look at hash or hash techniques or hashing files. Okay. Right. So we'll be starting at 10:40. Okay, so now we move on to another type of files. Of course, the sorted files we will look at in detail later. Like we will look at what is primary index file, secondary index file, right? As clustered file and so on. But let's look at another third type. Now we look at two type of files: heap files, node, just adding the records to the end. A sorted file where we keep the file in a particular field sorted order. The third approach is we use hashing techniques to access the file, access the records, or access the block. Remember, the smallest unit of access is block. So when you want to when you want to find a particular record, if you use hash techniques to find the record and also store, we call it hash technique or hash file. Okay. So what is a hash? So hash we'll look at in data structures and algorithms also. Hash is a technique where we map large number of range to a small number of range. Say this is 100, say 1000. We want to map it to one of the 10, 0 to 9. Say 0 to 1000 or 1 to 1000. Maybe we want to map it to 0 to 9. So bigger range is mapped to a smaller range is called hashing. Right? So when you map bigger range to a smaller range, there's a possibility of collisions because that is obvious. Okay. Then we have techniques to manage collisions as well. Okay. So there are hash functions that map bigger range to a smaller range. And what we do is we use a hash function together with one of the field. Usually it is the primary key, like employee number, student number, and so on. So maybe we will be having primary keys, say 1 to 1000, values from 1 to 1000, but maybe we have 10 blocks, 0 to 9 blocks. So that hash function will always convert any of these values from 1 to 1000 between 0 to 9. And then if that hash function says it is 3, that record is in the third block. If the hash function converts, say my employee number is 857, if my hash function convert it to 6, so that record is in the 6th block. Okay, so that is the idea. So then the advantage is when you insert, we insert it to the proper block, right? And therefore, when we search also, we get the same block number. So then we straight away load that block, and that block must be having the data. So that is super simple, super efficient, because just one block access is needed to get the data. Because your hash function says which block your record is. You don't have to sequentially search. You don't have to do binary search. You straight away load the block. So that is the advantage of using hashing technique. So the field that we use for hashing is called the hash key. And of course, we need to have a hash algorithm or hash function. So there are plenty of hash functions, very simple ones, more sophisticated ones, and so on. Right? Your hash functions will give you which this block your record is. Because when you insert also, we use the same hash functions to calculate which block you are going to save it. Okay. Right. So do this activity because we want to do the activities also. Take 1 minute. Sorry, 30 seconds because it's just 5 questions are there. Now in semester 3, a lot of students find data management difficult because you can't understand this at the last moment. Okay, so you have to prepare for these subjects up front. Okay, up front. Otherwise, you have to do this 2 times, 3 times. Right? Data management subject. It is not like other subjects where you can quickly get it. It absorbs slowly. Right, so let's do it. The is an extra byte that is stored with a record which will get updated when a record is deleted. So that is sort of a delete marker or something like that. I don't know exact words. You can get it from the note. Right? Delete bit or something. So just 1 bit is enough. Right? If that bit says false, that is actually that record is deleted. Though the record is still there, you have to consider it as a deleted record. Okay. So you can find that word, exact word from somewhere, a delete mark or something, okay, or delete bit. Right, second one. A field which can generate an ordered sequential file by physically ordering the record is called. A field which can generate an ordered or sequential file by physically ordering the record is called sorted. Okay, field again. Which can generate an ordered or sequential file by physically ordering the record is called, how do you call that? Maybe the key field, but or maybe the sorted field. I think I don't know exact word they use. Yeah, maybe ordering field. Right. So we order use based on that field. So that is called ordering field. Okay. So that is the field we use to order the data. Right. Ordering field. Ordering field. The function which calculates the hash value of a field is called hash function. Okay, hash function. So there the field is called hash field. Okay, the field we use to calculate the hash value is called hash field. The field we use to sort is called ordering field. The function, searching for a record in a heap file is done by linear search, because heap file is not sorted. We have no other option. We have to do the linear search. But if it is sorted file, we can do binary search. Okay. So these questions are to check whether you have understood. Okay. Right. So let's move on to a little bit more about the hashing. So remember, hash function map a bigger range to a smaller range, because maybe I have one. We are keeping that we have 10,000 records, but we keep all those 10,000 records in maybe 5 blocks, so that each of the possible value for your hash field must return one of the value from say 1 to 5. So those are called hash functions. So hashing techniques. So these hashing techniques we can subdivide into internal hashing and external hashing. Okay, internal hashing and external hashing. So internal hashing means you keep it in a internal file. Okay, or sometimes you can keep it in the memory also. Then we call it hash table. Right, hash table. So they have given you different methods for hashing. Like they have called it method 1, method 2, right? Method 2, method 3, and so on. Right, method 3 and so on for internal hashing. And some possible issues with internal hashing and how to solve those issues in internal hashing. And then external hashing. Okay, external hashing. So I'm just showing you the big picture. Right. So otherwise, sometimes when you go from one slide to the other slide, you lose the you forget about what we are talking. Okay. Right. So let's look at what are the internal hashing techniques. Okay. So the one thing is we can keep it in a sort of an array. The hash values. Okay, hash values. But remember, we need to have a hashing algorithm also. Right? We need to have hashing algorithms also. So the most popular hashing algorithm is mod function. Right? For example, say I have 1,000 records, but I want to map it to one of the value from 0 to 9, because I keep all these 1,000 record in 10 blocks. So the easiest one is if you have the record n, or the value is n, so we can say something like n, or let's say k mod, say if you have 0 to 9, we can say k mod 10. So when you divide a number by 10, and remainder is always between 0 to 9. Right? So therefore, always if you say 550, mod value will give you 0. If it is 784, mod 10 will give you 4. So that means it must be in the 4th block. This must be in the 0th block. If your record hash field says say 852, so mod 10 is 2. So that must be in the 2nd block. And we assume that a block can keep maybe at least about 10 records or 100 records in this case, because we have 1000. But it doesn't mean that, yeah. So if you have 100 records in a block, then we can always facilitate, right? We can always facilitate because we get maximum 100 records per a block, because only 100 records, if you have 1000 records, only 100 records will give you map to of one particular block. Okay, one particular block. So that is your mod function is the most popular hash function, but there are some other hash functions. The idea is to make it randomized. Otherwise, what happens is more records will come to a particular block, then that block is full, while the other blocks are not full. So therefore, we want to make sure that our hash function evenly distribute the records, or as much as possible evenly distribute the record. Otherwise, some blocks will be filled and some other blocks will be having plenty of spaces. Okay. Right. So we can use something like a mod function, very simple then, or we can use some more complicated hash functions, right, with some more sophisticated techniques used. Okay. So this is just example. This one also use a mod function, but it use some more additional calculations to make it more randomized. Okay. Right. So this is another technique they have mentioned in hashing, folding mechanism. So we look at the mod mechanism, then the folding mechanism. In folding mechanism, you take, or you can something like break your field into subpart. Right. Say this is my, say, NIC number. You break it into subpart. We want to make it more randomized. So maybe we can XOR these 3 fields and then do the mod operation, or add these values and do the mod operation, and so on, right? So then we call it folding. So then maybe we can do the mod operation. So rather than simply do the mod operation, so that is to make it more randomized, Okay. And when you do the hashing, the possibility of collision is there. Collision means multiple records get into the same value. Of course, that is okay in some cases. Of course, for example, if my block can keep, say, 15 records. So 15 value records getting into the same block key is okay, because I have the space, that block has space. But if you get more than 15 records are mapping to the same block, now we have a collision, because already this block is filled. Right? So in that kind of a situation, we need to have a collision resolution techniques. Right? That means we need to find another location, because this location is already filled. Okay. Maybe some other blocks have empty spaces. Or we have to have some extra block ready for in case of collisions. So there are 2 approaches. We have extra blocks ready for collision management, or we just look for some other block and put it there. Okay. So those are different techniques in managing collision. So collision is record, when I calculate the hash, that is happens in insertions. Okay. Inserting, not update and delete and so on. When you insert, you get a hash functions give you a block number, but that block is already filled by records. So then it's a collision. So then we need to manage that collision. So we call it collision resolution techniques. That is finding another location. Okay. Right. So these are some possible collision management techniques: open addressing, chaining, multiple hashing. Okay. So what are these three techniques? Open addressing means if a particular, now you get from your hashing algorithm, you get a block number, but that block is filled. So then you keep looking for the next block, next block, next block, and see whether it is empty. If you have empty space, you can put your record there. So that is called open addressing. The program scans the subsequent locations in order until an unused position is discovered. Right? So this can be done within the block also. That is, you try to insert a record in the block, but or we are doing this for the next block at block level. Okay, so that is called open addressing. So another technique is chaining. So chaining the pointer of the occupied hash address location to the address of the new record in an unused overflow location. So that is, if this is filled, you chain that block into another block. Okay, so then when this is filled, your new record is not, obviously you can't keep it there, maybe you keep it there, but this block is chained to that block. So therefore, when someone is searching for record also, they first look at this block, and then they look at this block because this is chained to this one. Okay, so maybe this is a brand new block, or maybe this is changed to a different block. Most of the time, those are brand new block, additional blocks available. Okay, so that is called chaining. The third one is also very interesting one, multiple hashing. So we use not one hashing algorithm, maybe different hashing algorithms also. So if the first hashing algorithm gives you a number, if it is already filled or there's a collision, then we are not looking for the next connected block or looking for the subsequent blocks. We use a different hashing. So second hash function, because first hash functions give us a collision. So then we use the second hash function, which is different from the first hash function. Maybe it gives you a block which is having empty spaces. So then you save it there in that block. But in that case, you have to keep track that we use not the first approach, the second approach. That is overhead. Okay, because when you retrieve the record, you have to use the second hashing function, not the first hashing function, because the first hashing function will give you connect you to the different block. That is not where your record is. Your record is in a different block, because you have to keep track that for this particular hash value or key value, we use the second or third hashing function, not the first one. So therefore, this one has a little bit of overhead as well, because we have to track which hashing function is used. Or else, if the first hashing function used and you just use the first hashing and check, if it is not there, then you have to use the second hashing function and again check whether is it there. So when you are searching for something, you use the first hashing function and go to the block and search. And if it is not there, then you have to use the second hashing function and again go to that block and search. And if it is still not there, only you know that it is not there, or otherwise you will find the record there. Okay. So that is multiple hashing. So you can go for open addressing, that is scan for the next available block, or chaining where your current field block is chained to another block, or multiple hashing where you are not using only one hash function. If one first hash function result in a collision, we use the second and third. And searching also, if first search results block doesn't give you the report, you have to do the second hashing and again go there and search there in that place also. Okay. Right. Any questions? Right. So those are internal hashing techniques and possible issues and possible solutions for collisions. So we look at the techniques, a possible issue of collision, and some possible solutions, that is chaining, multiple hashing, and open addressing. Okay. So the second approach is called external hashing. Right? External hashing. So it's only very small differences there, right? Though we just call it internal and external. So in the internal hashing, your hash function gives you the block. Okay, gives you the block. Or you can use internal hashing inside your block to find the records as well. Right? So those are all loaded words. But when it comes to external hashing, you have set of blocks considered as one bucket. So you don't get the block number, rather you get a bucket number. Your hash function returns bucket number. Okay. And internally you must know which bucket number is, so you must have a mapping between your bucket number 1 is for block number 1, 2, 3. Right? Maybe bucket number 2 refer to block number 4, 5, 6, and so on. So your hashing functions gives you a bucket number, and that bucket number has multiple blocks. Okay. So therefore, when you are looking for a record, you get the bucket number, then you have to look for the first block in that bucket. If it is not there, the second block in that bucket, and so on. Maybe you have 5 blocks in a bucket. So here the advantage is, since we have multiple blocks in a bucket, there's a lesser chance of collision because we have multiple blocks already in a bucket. So your hashing function says bucket 1. Now your bucket 1 has a bigger storage. Okay. But the disadvantage is you have to look for multiple blocks because your bucket has multiple blocks. Okay. So that is called external hashing. Right. So if you want, you can have internally for each bucket, you have another table that map your hash value to block, because you now come to the correct bucket. Now, rather than you searching for the blocks one by one inside the bucket, there's another table internally in the bucket level which map your hash field to the correct block. So that is another technique we can use. The bucket number is converted into matching this block address via a table in the file header. So now you have one approach to find the bucket number. So at bucket level, there's another technique to convert that bucket number, your field into the block level. Okay. Maybe that each bucket is separate subfiles and so on. So that possibility is also there. For us, it is one table. But sometimes if you have millions of records, internally it is mapped to multiple data files. Right? Maybe that each file is a one bucket. And inside that, there's another table to map it to the correct block, because each file can be in multiple blocks. And you can see a lot of things you have to think. And also examiner has a lot of space to ask different questions. So that is why a lot of students fail data management subject, because examiner has thousands of different ways to ask the question, change in the question. And all of a sudden, sometimes you completely lose it. Okay. So therefore, you have to spend time and concentrate on each and every important word in your note. That is why I'm just concentrating on your note itself, because it's a huge area, right? Huge area. So the So therefore, I thought, okay, I have given you a supplementary note. Still, I have not used it. But I try to use your note itself because your examiner set up the paper using this note, right? So this is a huge area. So I just try to stick to your note to make your life easier. Okay. Right. Even when we are doing bucket approach for external hashing, still there's a possibility of collisions. Okay. That possibility you can't eliminate, but we can reduce it because now your bucket has a bigger storage. And still you can use chaining and other techniques if you are still having collision at bucket level. Okay. But the idea is the collision problem is less severe because we have bigger buckets. Right? Bigger buckets. So that is the idea or the logic behind bucket for the external hashing. Okay. Right. So they have given another activity. Right. So let's do that also. I think this is a little bit difficult question. You may have to do a little bit of research also. But anyway, let's quickly go through it. So where is the term? The description is there, but the term is not there, right? And so they say match the description, but they have not given the words. But anyway, just read it and see whether you can find the word. Okay. Right. Just take 1 minute. Okay. Applying an arithmetic function such as addition or logical function such as exclusive or to distinct sections of the hash field. So that is folding. Right? You take distinct sections of your hash field and then apply some XO, add and so on to make it more mixing, randomize, and then apply the hash function to that value is called folding. So we look at that. The technique used for hashing where the program uses second hash function, if first hash function fails means it's collided, that is called multiple hashing. Okay, or double hashing, but I think better word is multiple hash. Yeah, multiple hashing. Okay. The instance when the value of a hash field of a newly inserted record hashes to an address that already contains another record, that is called collision. Right, collision. So that is not bucket. Sorry, the block number collision. That is internally within the block also you can use hashing, but it is very rarely used. But that is called collision. Okay. Starting with the occupied place given by the hash address, the program examines the succeeding locations or subsequent locations until an unused spot is located. It is called what? It is called open addressing. scan the subsequent location. Subsequent blocks are look for, put up that your record, right? So that is called open addressing. So these words are a little bit new to you, so it will take a little bit of time. A continuous group of disk blocks or single disk block which is comprising of the target address space, right? If it is a group of disk blocks, it is bucket. Okay, so it is called a bucket. That is what we use in external hashing. Okay. Bucket is a continuous group of disk blocks or single disk block. But usually it's not single block. Usually it is continuous disk blocks. Okay, set of blocks. Right. So now we move on to our most important topic, or the most challenging topic, that is indexing. Okay. So remember, we have three types of files. Heap file, we have sorted file, and then we have hash file, or we have the hashing technique. So some of the sorted file can be, the data file itself is sorted. So that means your data file itself is in the sorted order. But there are some situations, because we can sort a file only for a one field, sometimes we can have auxiliary index files. So those are sorted files having the sorted field and maybe access to the other major file. So those are called index files. So I told you that in the physical storage, we have the data file and index files. So that is what we are going to look at under indexing. Okay. So it's something like when you take a book, right? Physical book. Right. So let's take an example. It's something like you have an index in your book. So usually you have the index at the end. So this is the index, right? So if you want to quickly find something, so this is not a good index because it doesn't have a page, because this is the ebook version. So let's take a different PDF. Right. So this is like that. If I want to quickly find what is UNIVAC, I know that it is mentioned in page 10, right? Page 10. So it must be mentioned somewhere here. Okay. So index file, so it take bit of storage. So that is your book is your main file. Okay. This is your main file, your book, but your index take few more pages, right? Therefore, it take additional storage, but it make accessing a particular content much faster. So the advantage is you get another way of accessing your data. The disadvantage is it takes more storage because it's additional storage. But it's worth if you frequently use the index. Of course, if you don't use the index, it's additional work. And of course, you have to manage the index also. So there are two additional things. One thing is you need extra space. The second thing is when you insert a record to your data, you have to update the index in some cases. So therefore, those are the cons. The pros is you get another way of accessing your data because you have the index. Through index file, you can quickly go to the record. Okay. So that is what indexing is. Right. So indexes are used to speed up the record retrieval in response to specific search criteria. So if you are searching based on the index field, your index file is going to really handy. Okay. But it's an extra file, so you need extra space. And also you need to manage your indexes. Otherwise, your index will not having some missing things. Okay. So when you, especially when you insert and delete, you have to update the index. In some cases, if you update the index field, yes, whenever you insert, you have to update the index, right? And if you update the index field, you have to update the index file as well. But if you update something else, you don't have to come and update the index field in index file. Okay. Right. So when it comes to indexes or indices, we have different type of indexes. So we can subdivide it into single level indexes and multi-level indexes. So on the single level, we have primary index, secondary index, and clustering index. In multi-level indexes, we have the B trees, B plus trees. So then we have another type of indexes called hash index, logical index, multi-key index, bitmap index. Okay. So those are different type of indexes or indices. The plural of index is sometimes we use indexes, but the formal word is indices. Okay. But I frequently use indexes because it's easy. You can see even your notes sometimes use indexes. Okay. Right. So this is the main classification: primary index, secondary index, and clustering index. Right. So this we first look at this classification. Okay. Primary index, clustering index, secondary index. And these are all single level indexes. So you have to keep track of this. Otherwise, you get confused. Single level means it's one file. You don't have go to one index file and go to another index file and get into the data. So that is a multiple level indexes. So we are just looking at go to one index file, and then from index file we go to the data file. Okay, single level. Right. So there are three possibilities: primary index, secondary index, clustering index. Okay. So what is mean by primary index? This is super easy, but you have to understand properly. Primary index is our data file is sorted, physically sorted on the primary field or primary key field. So that is usually we sort our data file, right? Sort our data file based on the primary key field. Okay. Physically ordered. So then we say that we have a primary index. Right? Primary index. And of course, we know that primary key is unique. You can't have the same value twice in primary key. So therefore, primary index is always give you a unique value. Okay. So the second, now remember, your data file is physically sorted. Right? Physically sorted. So second approach or second possibility is clustering index. Okay. So in clustering index, you physically sort your data file not by your primary key, but by a different key, which is very rare. Right. So very rare to have clustering indexes. Okay. So usually you order your data file by primary key, or you have the primary index. But if there's a special need, you can order your data file by a different field, maybe sorted by or ordered by department number. So then department 1 records are here, department 2 records are next, and so on. When you insert also, you insert, if there's another employee with department 1, you insert it to here. So that is called clustering index. Okay. Order field is a non-key field. Physically order field is non-key field. Okay. Physically order. Physically order means your data file is ordered like that. So therefore, now you can see that you can have either primary index or clustering index. You can't have both because you can't order by both employee number and department number. Either you order by employee number, then primary index, or maybe you order by department number, then it's a clustering index. Or maybe you order it by email address. So then, because you are ordering your data file, so you can have only one of the primary index or clustering index, and most of the time you will have primary index. Very rarely, yes, if there's a frequently you search by say email address or name, yes, you can go for clustering index, but very rare, because you know that especially when you join tables, we always join by primary key. Right? So you have to think about the possibility of joining also. So in that case, most of the time, the ideal one is primary index. Okay. But as I told you, there's a possibility of frequently we are doing querying for another field, then you can go for clustering. But you can't have both. Okay. You can't have both. Okay. So you can see maximum of one physical ordering can be done. So therefore, you can have one primary index or one clustering index. You can't have both. Right? It cannot hold both primary index and clustering index. So that is very, very important thing for you to understand, and it's super easy to understand, but you have to pay attention to these statements. Okay. But when it comes to secondary index is a secondary mean of accessing your data file. So that means basically we have a different index file. So therefore, when you have a primary index or clustering index, of course, you can have only one of those. You can have any number of secondary indexes. Right? You can have any number of secondary indexes. You can have, say, you are using primary index based on employee number. You can have secondary index file for department ID, maybe for email address, and even maybe something like salary. You can have any number of secondary indexes, but the more you have secondary indexes, you can use those different index files to speed up the search and queries, but you need more storage. And also when you update a record, sometimes you have to update not only the data file, you have to update some of those index files. And of course, whenever there's insert, you have to update not only the data file, you have to update the index files. Okay, so there's overhead, but these are secondary indexes, secondary files. So therefore, you can have multiple secondary indexes, right? Multiple secondary indexes. Okay. Right. So we will look at in more detail about how these indexes are organized, and we have to do some calculations also, especially when it comes to access time. We need to do some calculation what is the time taken for access a particular record, if you are using a primary index, if you are using a secondary index, if you are using a clustering index, and additional storage, and so on. Because sometimes, not sometimes, first we have to go and find the particular block in the secondary index, and then you have to go to the primary data file, and so on. So there are some calculations we have to do, right? It needs a little bit of more time for you to understand that. And we will look at those things. And again, the block factor and those things are there. And also you must know whether we are doing linear search, whether we are doing binary search. So then you must know that the average, the worst case time taken, the log2 function, and so on. Right? We'll do those calculations next time. So then things get even more challenging when we move into the multi-level indexes, because first you do the search in the first index file and then you go to the next index file. Okay, so therefore make sure that you again go through the note today, understand the concepts properly, especially the latter part like indices and so on, hashing techniques, because we can combine hashing and indexes also. Next time, definitely we will be able to finish this topic. But next time we are going to do a lot of calculations, a lot of complicated parts we are going to handle in the next class. Okay, right. So we stop at this point. Right. So next time we can finish the this part in this indices. So then more than half of your data management is done. Okay. Right. We stop at this point.